Angles and radian measure. A brief review. The rectangular coordinate system. The rectangular coordinate system consists of a horizontal number line, an x-axis, and a vertical line. The y-axis intersecting at their 0 point is the origin. Each point in the system corresponds to an ordered pair of real numbers, x, y. The first number is the x-coordinate. The second number is the y-coordinate. The axis is divided into 4 quarters called quadrants. The point located on the axis are not in any quadrant. So notice in quadrant 1, both x and y are positive. In quadrant 2, x is negative, y is positive. In quadrant 3, x is negative, y is negative. And in quadrant 4, x is positive, y is negative. That's very important as we continue with this course. In trig, the angle consists of 2 rays in a plane with a common endpoint or 2 line segment with a common endpoint. These 2 rays or segments are the sides of an angle, and the common endpoint is the vertex of the angle. Associated with an angle is its measure, generated by a rotation about the vertex. This measure is determined by rotating a ray starting at one side of the angle, which is the initial side, to the position of the other side, the terminal side. Standard position of an angle. This is so important. An angle is in standard position if the first thing is the vertex is at the origin and the rectangular coordinate system, and its initial side, the initial side is along the positive x-axis. In other words, the vertex is at the origin right there, and the initial side is at the positive x-axis. A counterclockwise rotation generates a positive measure. So notice once again that the initial side is, right here's the vertex at the origin. The initial side is along the positive x-axis, and the terminal side is right here. And if you look up and around in a counterclockwise position, it's going to be a positive measure. And a clockwise rotation generates a negative measure. So once again, right here is the vertex. Right here is the initial side along the positive x-axis. And this is considered the terminal side. And my rotation is clockwise. And so it's going to be a negative measure. The rotation can consist of more than one complete revolution. An angle in standard position is said to lie in the quadrant in which the terminal side lies. For example, on this first figure, this one lies in quadrant 2 because the terminal side lands in quadrant 2. And in the second figure, notice that because the terminal side is in quadrant 3, this would be considered in quadrant 3. An angle is called a quadrantal angle if its terminal side lies on the x-axis or on the y-axis. Angle beta is an example of a quadrantal angle. So anytime it lands on one of the axes, like this one, notice once again the vertex is at the origin, the initial side is on the positive x-axis, and the terminal side lands on the y-axis, so this is called a quadrantal angle. The most common unit for measuring angle is degree. The figure below shows the range of angle measure for each quadrant when it's between 0 and 360. So notice in quadrant 1, theta is between 0 and 90. In quadrant 2, it's 90 to 180 degrees. In quadrant 3, it's 180 degrees to 270. And in quadrant 4, it's 270 to 360. Notice 0 degrees and 360 is in the same position. An angle measuring exactly 90 degrees is a right angle. An angle measuring between 0 and 90 is an acute angle. An angle measuring more than 90 degrees but less than 180 is an obtuse angle. And an angle exactly 180 is a straight angle. If the sum of the measure of two positive angles is 90 degrees, then the angles are complementary, and angles are complement of each other. Two positive angles with the measure whose sum is 180 degrees are supplementary, and angles are supplements. To use degree measures, we assign 360 degrees to complete rotation of a ray. 1 degree written 1 degree represents 1 over 360 of a rotation. Traditionally, portions of a degree have been measured with minutes and seconds. 1 minute is written 1 apostrophe is 1 over 60 degrees of a degree. 1 second is written with 1 with 2 apostrophe is 1 over 60 of a minute, or 1 over 3600 degrees. The measure 14 degrees, 36 minutes, and 24 seconds represents 14 degrees, 36 minutes, 24 seconds. Many calculators have a key for changing angle from degree, minutes, and second. Notation is DMS to a decimal form and vice versa. If you're using a graphing calculator, that button is under second, angle, and then you'll find the DMS button. You can also look for the degree, the minute symbol as well in the same second angle button. Angle sum of a triangle. The sum of the measure of an angle of a triangle is 180 degrees. An angle whose vertex is at the center of the circle is called a central angle. The radian measure of a central angle of a circle is the length of the intercepted arc divided by the circle's radius. 1 radian is a measure of central angle of a circle that intercepts an arc equal in length to the radius of a circle. Consider an arc of a length s on a circle of radius r. The measure of a central angle theta that intercepts the arc is theta is equal to s over r radians. The ratio s over r is a pure number, where s and r are expressed in the same unit. Thus, the radians is not a unit of measure like feet or centimeters. Example, a central angle theta is a circle of radius 12 feet intercepted by an arc length of 42 feet. What is the radian measure of theta? So we have that theta is equal to s over r. So theta is equal to, we have that the circle of radius is 12 feet and the arc length is 42 feet. So s is 42, r is 12, is equal to 3.5 radians. Example 2, a central angle theta in circle of radius is 6 feet, intercepted at an arc length of 15. So the arc length is 15. What is the radian measure of theta? So theta is equal to s over r. So theta is equal to 15 over 6, which is 2.5. Use the basic relationship pi radians equals 180 degrees. To convert degrees to radians, multiply degrees by pi radians over 180 degrees. To convert radians to degree measure, multiply radians by 180 degrees over pi radians. So convert each degree measure to radians. So 60 degrees. So the way you can remember is you have 60 degrees and you're using dimension analysis kind of. So we're going to say 60 degrees times, and the ratio we're going to pick here is we want the degree symbol on the denominator still and cancel out. So that's how you can remember the formula if you need to. So we're going to multiply by pi over 180 degrees. And once again, the unit degrees cancels out. So we have 60 pi over 180. Now, for those of you that want to use your calculator to simplify the fraction, you can hit math fraction without the pi symbol. So what you can do is hit 60 divided by 180 and then hit math. And then the first option is fraction, so that's going to give you 1/3 pi, or simply pi over 3. Example 4, convert negative 90 degrees to radians. So we have negative 90 degrees. We're going to multiply by pi over 180 degrees. Notice the degrees cancels out, so we have negative 90 pi over 180. Once again, you can hit negative 90 divided by 180, hit enter, hit math fraction, that's negative 1/2 pi, or you can say negative pi over 2. Example 5, we're going to convert 270 degrees to radians. We're going to multiply by pi over 180 degrees. Notice the degree symbol cancels out. So we have 270 pi over 180. Whenever I'm using the calculator, I never put the pi. I just put 270 divided by 180, hit the math fraction button, and we get 3 over 2 pi. So that's basically 3 pi over 2. Example 6, we're going to convert now a radian measure, 2 pi over 3, to degrees. So we know we're going to multiply by 180 degrees because I need it to be in degrees at the end, over pi. So notice the pi's have to cancel out, which they do. So then we can just say 2 times 180, which is 360 degrees, over 3, and that gives me 120 degrees. Example 7, we're going to convert radian measure to degrees. Negative pi over 6 times 180 degrees over pi. Notice the pi's cancel out. And we have negative 180 degrees over 6 is negative 30 degrees. Example 8, we're going to convert pi to degrees. So we have pi times 180 degrees over pi. Notice the pi's cancel out. So pi is equivalent to 180 degrees. The figure illustrated that when the terminal side makes a 1 full revolution, it forms an angle whose radian measure is 2 pi. The figure shows the quadrantal angles formed by 3/4, half, and 1/4 of a revolution. Notice 1 revolution is 2 pi radian. 3/4 of a revolution, notice is 3/4 times pi, which is 3 times 2, which is 6 pi over 4, which is equal to 3 pi over 2. Notice where it lands. One half of a revolution is 1/2 times 2 pi. Notice the 2's cancels out, leaving me with pi radians. So notice that this is pi radians. And 1/4 of a revolution, 1/4 times 2 pi, but 2 pi over 4 is 1/2 pi. So notice that this is the position for pi over 2. Positive angles in terms of a revolution of the angle's terminal side around the origin. 1/12 revolution, so 1/12 times 2 pi is pi over 6, which is equivalent to 30 degrees. 1/8 of a revolution is 1/8 times 2 pi, which is pi over 4, which is 45 degrees. 1/6 times 2 pi is pi over 6, which is equivalent to 60 degrees. 1/4 times 2 pi is pi over 2, which is equivalent to 90 degrees. and 1/3 times 2 pi is 2 pi over 3, which is equivalent to 120 degrees. A complete rotation of a ray results in an angle measuring 360. By continuing, the rotation angles of a measure larger than 360 can be produced. Note, the angles 60 degrees and 420 have the same initial side and same terminal side, but different amount of rotations. Such angles are coterminal angles. Their measures differ by a multiple of 360. Two angles with the same initial and terminal side but possibly different rotations are called coterminal angles. Increasing or decreasing the degree measurement of angle in standard position by an integer multiple of 360 results in a coterminal angle. Thus, an angle of theta is coterminal with an angle of theta plus 360k, where k is any integer, or minus 360k. Increasing or decreasing the radian measure of an angle by integer multiple of 2 pi results in a coterminal angle. Thus, the angle of theta radian is coterminal angles of theta plus or minus 2 pi k, where k is any integer. We're going to sketch each angle in standard position, draw an arrow representing the correct amount of rotation, find the measure of the other angle, one positive, one negative, that are coterminal with the given angle, and then give the quadrant for each. And then we're going to also tell the degrees. So sometimes it might be easy for some people to think in terms of degrees. Whatever works for you, that's the best way to work it. So if you don't like 2 pi over 3, you can always convert that to degree first. So if we converted 2 pi over 3 to degrees, I would multiply by 180 over pi, and notice the pi's cancel out. 2 times 180 is 360 divided by 3, so we know it's 120 degrees. So we know that it's 120 degrees for this. We've also talked about this is 0 degrees. This is 90 degrees, which is equivalent to pi over 2. This is pi, which is equivalent to 180. This is 3 pi over 2. And this is, which is 270 degrees. And then we're at back to 360 or 2 pi. So here, 120 degrees or 2 pi over 3. So we know we're in quadrant 2. So here's my vertex, my initial side, and my terminal side is in quadrant 2. And I need my angle to be in the positive direction, so it's counterclockwise, and that is my angle 2 pi over 3. So my positive coterminal angle to 2 pi over 3 would be 2 pi over 3 plus 2 pi. We're just adding 2 pi, so in other words, we're going to go around all the way one time and then come back around. So in your calculator, if you don't like fractions, remember you have to have a common denominator. So you can say 2/3 plus 2, and then hit the math fraction button and get 8/3. So it would be 8 pi over 3. Remember, you have to get a common denominator to add and subtract fractions. Negative coterminal would be 2 pi over 3 minus 2 pi. So in the calculator, hit 2/3 minus 2. Hit the math fraction button. You get negative 4/3. So it would be negative 4 pi over 3. And notice this is in quadrant 2. Negative 120. So notice that in example 8, we ended up getting that it was 120 degrees. Well, negative 120 degrees is going to be clockwise when we graph it. So the positions is not the same positions. So here's the vertex. Here is the initial side, and we're kind of working backwards. So this is 0 degrees. This is going to be negative 90 degrees. This is negative 180 degrees. negative 270 degrees, and then it's going to be back to 0 degrees or negative 360. So we're going backwards, and so negative 120 would be in quadrant 3, and it's going clockwise. Now, let's say you didn't like the way I did that. Another way you could have done this is you could have said negative 120 plus 360 is equal to 240 degrees. And notice that that is in the same spot. For 240 degrees is in quadrant 3. For negative coterminal, it's going to be negative 120 minus 360. That's negative 140 degrees. That's going to go around one time all the way and then land back at negative 120 degrees. And in radian measure, negative 120 degrees times pi over 180 is going to be negative 120 pi over 180. Once again, hit the math fraction button, hit negative 120 divided by 180. Hit the math fraction button, you'll get negative 2/3, so it'd be negative 2 pi over 3. Example 10, negative 240 degrees is going clockwise. Once again, so here's the vertex. Here is the initial side. We know we're going clockwise, so we know we're going that way. So if you can't figure out where negative 240 is because you don't want to count backwards, you can always find the positive coterminal angle first by adding 360. So negative 240 degrees plus 360 degrees gives me 120 degrees. And we know 120 is in quadrant 2. However, this is negative 240 is going to be clockwise and land in the same position as 120. So you can always think backwards and do it this way. Find the positive coterminal angle first. Negative coterminal of negative 240, we're going to subtract 360 to get negative 600 degrees. And notice that we're in quadrant 2 because the terminal side lands in quadrant 2. And for radians, it's going to be negative 240 degrees times pi over 180. So you can say negative 240 divided by 180 pi, and that simplifies to negative 4 pi over 3. Example 11, 515 degrees. Notice that's going to be more than 360, which means it does one-time rotation and then it stops. And so where it stops is what we're going to find out. So we can say 515 degrees minus 360 degrees equals 155 degrees. So we know we're in quadrant 2. So once again, this particular problem here is the origin. Here's the initial side. It is going counterclockwise because it's a positive angle. So we're looking up and around. We're going around all the way one time. So that's 360 and then a little bit more to 155. So we're at 515 now. And notice we're exactly in quadrant 2. For the negative angle, we're going to say 515. When we subtracted 360, we got 155. So you have to subtract 360 twice to get negative 205 degrees. And then for radian measure, we have 515 degrees times pi over 180. So we have 515 pi over 180, and if you hit 515 divided by 180 and hit math fraction in the calculator, that will give me 103 pi divided by 36. Example 12, pi. So if you don't know exactly what pi is, by now you should know that pi is equivalent to 180 degrees, and you can actually convert that by saying pi times 180 divided by pi, and notice the pi's cancel out, so that's equal to 180 degrees. So now on, anytime you see pi, you can always substitute 180 for pi to convert real quickly in your mind. So we're going to start with our origin, the initial side. We are going counterclockwise to 180 degrees, and this is the terminal side. This is no quadrant. It's actually called a quadrantal angle, so this is no quadrant. This is actually called a quadrantal angle. For positive coterminal, it's going to be pi plus 2 pi, which is equal to 3 pi. Remember, pi is equivalent to 360. And then for negative coterminal, it's going to be pi minus 2 pi to give me negative pi. For example 13, we are going clockwise because it's a negative angle. So here's my origin, my initial side, and we're going clockwise. Well, if you don't know what negative 7 pi over 2 is, you can always convert first. Remember, we just said that pi is 180, so now you can just say negative 7 times 180 degrees divided by 2, and that will give me negative 630 degrees. So now, there's two ways to figure out the positive coterminal. One way is you can go ahead and say negative 7 pi over 2 plus 2 pi. When you get a common denominator, that's negative 7 pi over 2 plus 4 pi over 2. And that gives me negative 3 pi over 2. And we're going to have to add another 2 pi. So when I do another 2 pi, we have negative 3 pi over 2 plus 4 pi over 2, and that will give me pi over 2. So we're at pi over 2. So this is also a quadrantal angle, so there's no quadrant here. But this particular one went around one time clockwise, and then it stops at negative 7 pi over 2, or pi over 2. And if you didn't like that concept, you could have taken 630 degrees and added 360 twice, and you would have got 90 degrees. And remember, that's the same thing as pi over 2. For the negative coterminal, when we added one time 2 pi, we got negative 3 pi over 2. So we don't need to do that again. We already did that by saying negative 7 pi over 2 plus 2 pi is equal to negative 7 pi over 2 plus 4 pi over 2. Well, that's negative 3 pi over 2. So we already had a negative coterminal when we added basically 2 pi one time. Degrees and radian measures of an angle commonly seen in trig. So this is a good unit circle to memorize. Notice that 0, 90, 180, 270 is basically the ones that you definitely want to memorize. And then that's equivalent to 0, pi over 2, pi, 3 pi over 2, and then back to 0. And then also you need to remember the 30, 45, and 60, which is equivalent to 30 is equivalent to pi over 6, 45 is pi over 4, and 60 is pi over 3. So, and then the rest are just the multiples of those. Notice once again, if it's going clockwise, it's a negative angle, and if it's counterclockwise, it's a positive angle. Let r be the radius of a circle and theta be a non-negative radian measure of a central angle of a circle. Then the length of the arc is intercepted by s is equal to r theta. Earlier we found the angle, now we're finding the arc length. So a circle has a radius of 2.3 centimeters. Find the length of the arc intercepted by the angle of the following measure, 2 pi over 3 radians. I do want to point out that here that we must have theta in radian measure, and if you don't, you have to convert it to radian measure before you use the formula. So here we have 2 pi over 3 radians. So S is equal to R theta. So we have that R is 12.3 and theta, we're going to say times 2 pi over 3. So we're going to do 12.3 times 2 and divided by 3. So it would be 8.2 pi. And if they want you to actually type in as a decimal answer, it would be 25. So 8.2 times pi is 25.76 centimeters if they ask you to round to 2 decimal places. Example 15, we have 135 degrees. So in order to use S equals R theta, theta must be in radians. So we're going to multiply by pi over 180. So 135 over 180, I'm going to hit math fraction to convert that. That gives me 3 pi over 4 is my theta. So S is equal to R times theta. So R is 10. Theta is 3 pi over 4. So that gives me 30 over 4, which is 7.5 pi. And 7.5 times pi is 23.56. A circle has a radius of 13. Find the length of the arc intercepted by the central angle having each of the following measures, 5 pi over 6 radians. So we have that S is R theta. S is equal to R is 13 times theta is 5 pi over 6. So S is equal to 13 times 5 divided by 6. So we have 65 over 6. And since it's repeating decimal, I didn't round that. And then if we say times pi, and we need to approximate it to 2 decimal places, that gives me 34.03. Now, I rounded to 2 decimal places, so make sure you read what my math lab says. Example 17, 60 degrees. So we have that S is equal to R theta, but theta needs to be in terms of radians. So this is 60 pi over 180. That simplifies to pi over 3. So we have S is equal to R theta. 18 times pi over 3 is 6 pi. And 6 times pi is 18.85 if I'm rounding to 2 decimal places. Area of a sector. The area of a sector of a circle of radius r in a central angle of theta given by the following: A equals 1/2 r squared theta, where theta is in radians. This formula is used to find area of a sector. Once again, theta must be in radians to apply the formula. So we have find the area of a sector of a circle radius r with the central angle. So we have A is equal to 1/2 r squared theta. Our area is equal to 1/2. R is 14.6 squared, and theta is pi over 8. So area is equal to, I'm going to punch that straight in the calculator. We have 1/2 times parentheses 14.6, close the parentheses, square it, times pi over 8. And I get 41.85, and this would be whatever unit squared, since we're talking about area. And once again, I rounded to 2 decimal places. Example 19, when we're finding the area of a sector, which is, the formula is A equals 1/2 r squared theta. Here we have that A is equal to 1/2, r is 11.6 squared. Well, notice theta is not in radians, so first we need to convert the 85 degrees. So it's going to be 85 times pi over 180. So 85 divided by 180, and I'm going to hit the math fraction, and that gives me 17 pi over 36. So A is equal to 1/2, parentheses 11.6 squared, times 17 pi over 36, close the parentheses, hit enter, 99.81. Linear speed. Suppose P moves along a constant speed along the circle of a radius and a center O. The measure of how fast the position P is changing is linear speed. If V represents the linear speed, speed is equal to distance over time. So V is equal to S over T. Once again, P moves at a constant speed along the circle, where S is the length of the arc traced by the point P at a time. Angular speed is at a point P in the figure below. Moves along the circle ray. OP rotates around the origin, and since OP is on the terminal side of the angle POB, the measure of the angle changes as P moves along the circle. The measure of how fast the angle is changing is an angular speed. So angular speed is equal to theta over t, where theta is in radians. So here, theta's measure of angle POB at time. As with the earlier formula in this chapter, theta must be measured in radians, with angular is expressed in radians per unit of time. Angular speed is equal to theta over t, where theta is in radian. Linear speed is S over t, or you can say, since S is r theta over t, or linear speed is r over the angular speed. The angular speed of a point Earth is pi over 12 radian per hour. So this has given us that angular speed is pi over 12. This is radians per hour. The equator lies on a circle of a radius approximately 4,000 miles. So r is 4,000 miles. Find the linear speed in miles per hour of a point on the equator. So we want to find the linear speed. Well, here we're given r and angular speed, so the radius. So we're going to use that the linear speed is equal to r times the angular speed. So linear speed is equal to 4,000 times pi over 12 So linear speed is 4,000 divided by 12. I'm going to hit the math fraction and I get 1,000 over 3 pi. And if I go ahead and multiply that by pi, which is equal to 1,047.